Hi, cpsc 386. I want to show you a little project that I made to give you an idea of how we can use Pygame to make some really cool stuff this semester. So let me start by telling you what I've got here. I know this is a Macintosh, but I did the development on Linux and made sure it works on Linux. So everything that I'm going to show you, I know is going to work 100% on Linux. I've done all that legwork up front. And I'll post this repository online if it's not posted already. Excuse me. So here I've got my, in my terminal, I've got this directory, and it's laid out very similarly to the previous project that I showed you last week, which was just showing you the idea of like how to make multiple scenes. Now, in this project, I'm going to have only one scene because I really want to focus on some gameplay mechanic or something that we can start using as the basis of a game. So I've got the README, of course. I've got my main in movedemo.py. I've got most of I essentially have all my source code in video game, and I've got my requirements over here. And I'm going to show you something new about how we can set up our virtual environment, and I'll make this nice and big and put it in the middle of the screen. So, wow, it's not working. Well, we had a little bit of a technical problem. Got that resolved, made the window nice and big and put it in the middle. Like I was saying, this is the layout of the project, and I want to do something a little bit different with creating my virtual environment. So let's start by creating that virtual environment. I'm going to activate that virtual environment. And everything is as it seems. I've got that directory with my virtual environment in it. I already have the requirements file, but I'm going to do this manually. So I'm going to install Pygame. I want Pylint. And is there anything else that we... No, I think that's all that we really need. It does that really fast. Now, what we did last time was that we didn't treat that as something that we installed. In fact, we did relative paths in our imports. I'm going to show you a little trick. If I do my pip freeze right now, and I don't redirect it to file, you can see that this is including Pygame and Pylint and its requirements for this environment. I can also install video game. Now, if I install video game, everything inside that directory, that folder, will be available to me to use anywhere I want inside my project. However, the gotcha is it will only it'll make a copy of it, and you won't be, if you make a change, it won't reload. So a little tip here is if you push a -E, it marks it as editable. When it's editable, that means if you make changes as you're developing, it will just magically reload the file. And this is a big time saver and makes life a lot easier for you. So if you do this, it's going to install the stuff that's in that folder video game into your virtual environment so that you can use it. Now, if you do the pip freeze right now, let's look at what the output is. Interestingly, what it's going to say is like, well, you just installed this directory, but it's not a directory because it's smart enough to recognize that it is a GitHub repository. And it's going to give you a link to that GitHub repository. In my case, I'm using SSH as the protocol, so that's why it says Git plus SSH. If I had cloned this repository using HTTPS, it would say HTTPS instead. But it has the path to the remote, and then it also has the hash for the version that I'm using. If you freeze this like it is right now, what's going to happen is it will always go back to this version. Instead, what I've done is inside my requirements file, let's make this nice and big. I want Pygame 2, I want Pylint, and then I just have a -E video game. This is all you need, and the next time I reconstruct my virtual environment from this requirements file, it will install this current version and make it editable so that as I make changes, it will reload these changes and make my life a lot easier as I develop whatever I'm developing. So that's the requirements file. Now, let's take a look at what this does. Now, I'm going to give you a word of warning. There are sound effects and sounds in this project. So if you're listening with headphones or earbuds, I recommend turning them down just to be on the safe side. So do that. I'll give you a moment to do that before I start running the program. I don't think the sounds are loud, but sometimes these things work out weird when you make a recording. So just a word of warning. Okay, so here we are. We've got a screen of dots. Now, if I click someplace, all the dots will go there. And if I click someplace else, all the dots go back. Nothing fancy. In fact, this was based off of one of the example programs in the Pygame directory. I just expanded it a little bit. And what we're using here is sprites for our dots, our balls that we have on the screen. We've got, we're processing events, so we're getting a coordinate from where we're clicking with the mouse. And it's event-based, where the balls themselves are smart enough to know that when an event occurs, for instance, a mouse click, they'll move back to where they were originally, or they will travel to that location that you just clicked on. The other thing that's going on is we're using, there's a concept of time and speed, right? So I can have different balls move at different speeds. And in fact, I invert the speed when I put them back to their original locations. We can also reset this as many times as we like to see different random patterns of dots. And then try it again. Again, nothing complicated. But this might be the start of, like, this is a mechanic that you perhaps could use for a video game or an effect inside of a game. Now let's take a look at how we made all this happen. Let me make this window a little smaller. Ideally, that's large enough for you to see on the video screen when you're watching this video. Again, our move demo is just like the previous demos where you're just importing from that video game module and then creating the object and running it. And then it just returns the value back to the operating system when it exits. Really simple. All the hard work is happening in these files. Let's put them in a line so we can look at it. This file, assets.py, is our asset manager. This is the little magical tool I have that I can say the name of something and it will locate the data that I want. All my binary data is stored in a directory called data. This isn't the best practice, but it's good enough for what we're doing here, and it keeps everything inside the repository. And we'll take a look at the asset manager in a second. We've got our game object right there, and I know I skipped over circle. I'll come back to it in a second. Our game.py contains the object which we're running right here. RGB colors, that's just a lot of colors. It's just so that you have some convenience of randomly selecting colors. I use this in this program because I want to have, I think 1,000 little circles on the screen, and I wanted a way to come up with random colors, and that file came in handy. I've got scene.py, which is going to be what we see on the screen. Scene manager.py is what I use to manage what is the first scene, second scene, third scene. In this situation, it is just one scene, so my scene manager is essentially just a list. Setup.py, we can ignore that. This is generated by Python. Let me circle back to what circle.py is. Circle.py is an important part of this demonstration because it shows us how we can work with surfaces and with sprites. So a surface is an image, or any pixels that we're going to show on the screen, we can call it a surface. Our screen is a surface, a sprite has a surface, and circle defines a surface where I color in a circle, and then it also defines a circle sprite, which is what we actually use on the screen for drawing and figuring out where they should move and how they should move. So let's start by taking a look at circle. Now, I'm using, again, TextMate, but you guys should use VS Code. VS Code is what all the cool kids are using. It's got all sorts of really cool bells and whistles that will make your life better. I like to use TextMate when I do stuff like this because it has a really clean interface and allows me to show you what's going on without extra buttons and doodads. So let's go up to the top. Our first class is, so again, we're importing Pygame and I'm using the RGB colors that's coming from video game. Here's our first encounter of where like installing video game, that folder, into our virtual environment saves us time and saves us energy because I can just say, hey, I know there's this file, I know there's this thing inside a video game. I can just say from video game, import that. And now I've got RGB colors available to me. This file has two classes. The first class is Circle Surface and the second class is Circle Sprite. Both of them inherit from Pygame classes. Now in class, I tried to load the Pygame website and it didn't work. What happened was I think I can recreate it. I went to this web page and it was gone. I don't know why it's gone. Doesn't matter. What's important is that you know how to get to the Pygame documentation. The Pygame documentation live at, and I'll put it here. Pygame documentation lives at pygame.org/docs. Bookmark this. Save this someplace because it's really important that you're able to read the documentation and get some tips about how you can use stuff. And the Pygame documentation is the first place to look. The second place to look oftentimes is the source code. However, like I pointed out in class, the source code for Pygame, a lot of it's in C. And so you just can't easily go and look at the C code to try to make sense of how you can do this in Python. So the other tip I have is that when you use the Pygame docs, and I'll just pick Surface because that's our first class that we're going to look at, and Surface is right there. When you read through this documentation, it does take a little bit of effort to understand how they're organizing it because sometimes you're not clear whether it's a data member, it's a class, or it's a function because they don't necessarily adhere to naming practices that I think fit naturally with PEP 8. But underneath everything that you look at, you could search for examples of something. So you can click, or you used to be able to click. I guess this is not working now. Oh, there it goes. You can click on this and it'll take you to GitHub and it will search for instances of somebody using Pygame Surface Blitz. And you can take a look at other people's code to say, hey, here's how you could use that and get insight into it. Now, oftentimes just looking at that one line is not enough. You're going to have to look at somebody's project. And so this is why I try to make my projects consistent and very similar to one another so that by looking at mine, you can get some insight into how they work and you've got one person that you can ask to explain how it works, which is me, rather than having to go through some stranger's code repository and try to make sense of what they're doing. And you don't really have a way of contacting them. Well, you could. There's just no guarantee that they're going to respond in a timely fashion. So please use the stuff that I provide you, plus the documentation and the time that we have in class and office hours to ask questions to understand how things are organized and how they work. And don't forget, bookmark this webpage so that you can easily find it. You don't have to do a search or look through your notes or something else. Okay, so back to what we were talking about. I made two classes, Circle Surface and Circle Sprite. We can think of a surface as an image. A surface is going to be a collection of pixels. A surface is something that we can draw into. And filling that surface with color can either come from loading it from a file, that's an image, or by doing some calculation, like drawing, that will fill that surface with some colors. Some basic operations that you have when you're coloring something is to say, hey, I've got this surface, I want to fill it with one solid color. I have this surface and I want to draw a polygon that has these points, connect them together and fill that with a color. I want to fill that surface with a line. Here's a series of points, connect each point together and fill that line with some color. These are operations that you could do with a surface. Now, this class here, I wanted a way to come up with a circle that I can draw on the screen. And so to draw the stuff on the screen, that's a player character or non-player character. So I want to think sprite. But before I get to that, I want to say, like, what does it visually look like? And that's what the surface is. The surface is the visual appearance of something, the image, the color. To define, let me make this a little wider. There we go. All right. To define this circle surface, I inherit from Pygame surface. And the information that I need to create the circle would be the radius, what color I'd like it, and I'm going to default to the background color being black. And I like to add a name or an ID so that in debugging, if I want to be able to print stuff out to the screen, I have ways of keeping track of what it is. So it's just like a unique identifier. The width, because surfaces are rectangular in shape. And so this circle is going to be inscribed in some type of rectangle. In this case, it's going to be a square because these are perfect circles. They're not ellipses. So the width and the height of this square will be 2 times the radius. So I'm going to initialize the parent class being the surface here, as being width by width. How did I come up with this? Well, let's go back to our documentation. Let's go to surface. And so Pygame surface, and here's where it tells us the constructors. Given the width and the height, or the width and height, and these flags, right, or this surface, you get a surface. This is the constructor that initializer that I'm using. I'm giving it the width, and this because I'm making a square. And these are all default values, so I don't have to worry about that. And I get back from that a surface. So here I've initialized my parent by giving it the dimensions of the surface. I need to figure out the center of the surface. So if you think about a square, well, if you start from the upper left-hand corner, I would go out radius units in the x direction and radius units in the y direction, and I will be able to end up at the center of that square. So the center location is coordinates relative to a corner of the surface, not your window. I assign the color that was passed to me. I assign the name that was given to me, and I fill the background of my surface with black. And then I use this function, Pygame draw circle, to fill myself with a certain color at that center and that radius. Oops. Let's take a look at how I came up with that. So Pygame draw, that's draw right here. I'll open this in another tab. You've got options like draw rect, draw polygon, draw circle, draw ellipse, draw arc. And so I use draw circle. And here, I use that. So this is going to give a surface. I provide the surface, in this case self, because I'm drawing onto myself right here. See that? The color, the center, and the radius, and it returns a rect. Now, I didn't save the rect on this line because the surface itself already has the rect. I don't need that information. I might want to save it, but I didn't need to. Some other things that I added was I created a property for myself that returns the radius of that circle. This allows me to say self.radius with no underscore, and anybody can ask me for my radius, so it's public. It looks and acts like an instance variable, but it actually is mapped onto this method. I ended up not needing those, and here is a convenience property for myself. Every surface has a method called getRect, and getRect will return the surface's rect. And I decided that it's more convenient for me to have a property that allows me be able to read that surface and get a pointer back to it. And so this ultimately is all this class is. Let me just get this out of the way so you can see. This class definition has an init, which creates a surface of a size that's proportional to made according to the radius of the circle. It initializes its parent, saves some data members into instance variables, so I have the color and the name, and I can get that back if I want to debug. and then draws into itself the circle using a convenience function from PyGameDraw. And I've got these two properties here for convenience for use elsewhere. That's this class. Now, PyGameSurface represents what something looks like. It's the surface. I now need something that is going to be something I can use to animate on the screen, something that I can use to collide with other things, something I can use to move according to some clock, some speed. And so here is where I make the circle sprite. Circle sprite inherits from PyGameSprite. These are class variables, so that all the circle sprites have a minimum speed of 0.25 and a maximum speed of 5. These are effectively magic numbers. I just selected them out of thin air, and it turned out that they were good choices because what I saw on the screen was interesting. You could come up with a little math if you need to, if you want to come up with what are good choices for the speed inside of a game. You just need to come up with some way of thinking about units in your coordinate system. So now I want to create a circle sprite, and the sprite's what I'm going to be drawing on the screen. So I need an initializer that's going to have a position. Now this position is a position that's inside the window. It needs to be placed somewhere on there. Let me run the program one more time so we can see what it looks like. Every single circle that you see is not touching another circle. There's a few pixels of space. In fact, I believe it's 3 pixels of space between or 3 units of space. I don't know if it's a pixel between itself and the other circles. And if I rebuild all my circles, you can find that they are always distributed so they're not touching. Each one of these circles need to have a position, and that's what that first parameter is. Speed is a value that tells you how fast that circle could move on the screen. Radius is the size of the circle that's going to be drawn on that sprite surface, and the color is the color that we're going to assign that circle. So circle surface is used by the sprite. So every sprite has a surface, and that's I assign the outcome of this initializer to the sprite's image. Oh, I forgot to mention, like anything, you have to initialize your parent. So you initialize your parent, and once the parent's initialized, well, that sprite has an image. We could load an image off the file system, but I thought as a starting point, we can just create our own surface and then assign that surface to ourselves. So now that sprite has that colored circle, and we're going to save our position as the original position. Because remember, when I click, all the balls will move to that point I clicked on. And then when I click again, all the balls will go back to the original position. So I need to save the original position. I ask the circle surface, remember circle surface was assigned to image, and now image is of type circle surface. I can ask the image for its rect. And then I assign the rect back to myself. So now my sprite, the circle sprite, takes on the same size or dimensions as the image I just created. So I have a one-to-one correspondence. I could have a sprite larger than the image. I can have an image larger than the sprite, but that just doesn't quite work out right. So what I'm going to do is I'm going to say if my circle surface is, let's say 100 pixels by 100 pixels, then the rect that I create for my sprite will also be the same size, 100 pixels by 100 pixels. I assign the center of my rect a position X and Y. Now, I put this note here because position that I pass in is a vector. Pygame has a math library, and inside the math library, there's different classes that you could use to do math, surprisingly. So they've got a vector type and a vector 3 type. Vector 2 type and a vector 3 type. The vector 2 type you can initialize with x and y or another vector or a single value, or this is what they're essentially saying here is give it a tuple, an xy tuple, and it'll return back a vector 2. What I like about using vectors rather than tuples or lists is I can do math with a vector. So I can do dot product, cross product, addition, find the length, normalize. All these operations are available to me when I use vectors, and they're not available to me when I use tuples. Rex, this thing right here, rect, does not have its center. Like if you look up the documentation for a rect, rects are defined as left top width and height, or as left top height width and height, like that. If you have a box, and let's just pick this window as the box, left would be the extremal value in this direction. Top would be the extremal value in this direction. And width and height would tell you how much in this direction and that direction to move. So you're essentially, I flipped it around. Left top would be this corner right here where my mouse is. Let me see if I can make it big. It's not getting big, but it's the upper left-hand corner. So this part right here where my mouse is grabbing the corner, that's your left top. And then width and height are how far to go in the width direction and how far to go in the height direction. That's how you define a rectangle. These are defined as tuples, not as vectors. So it's convenient information to know where this rectangle or this rectangle are inside the window, but they don't give me the facility to do addition, subtraction, dot product, cross product, length, all those things that are useful when I want to move things around. So this position that's coming in to the initializer comes from the little engine or the function I use to create random positions. That random position is a vector, and so I have to convert it to a tuple. It's a very simple thing to do. You just put the parentheses there to say it's a tuple and just pull out the value x and y. Now, once that's done, and this can be, remember what I've said before, Python allows good programmers to become bad and bad programmers to become even worse because there's no type hints, right? Like if I don't remember that position is a vector 2 and that center is a tuple, I can very easily do something funky here, which will then end up breaking in a weird way. So if you have the time and wherewithal, use type hints. If not, just be aware that you can very easily change the type of center by assigning it the wrong type position and then have something else break because center is no longer the type it expects. All right, now that we've gotten here, we're just going to have a safety check to make sure whatever speed that is passed in fits within our min and max of our speed. Assign it to speed. And if you're not familiar with assert is a way to do a sanity check. And at runtime, if this sanity check fails, it'll just stop the program. It'll throw an exception. It is a good way to make sure that if you've got different parts working together, that if you expect one part to feed in some value into another part or some object or whatever, you can make sure that you stay within the bounds of what you expect. That if you expect a non-null value, you expect the value to be greater than 10 or expect a value to be less than 100, assert that to be true. You say assert, and then you give a statement that will evaluate to true or false. And if it fails, it'll stop the program, and you can say, how did I go wrong? This is especially useful when you're not in the practice of like remembering your types. You can assert that, that center is of type such and such, or you can assert whatever it is that you want. Moving along, we collect our speed and radius, and for debugging, we collect our name. We don't really need to know the color because the color's passed to the circle. It makes the circle whatever. So now we've got properties for getting the radius. We have a property for getting the position. And this is where we go back from being a tuple, right? Because the position of my circle sprite is the rect center. That's what I'm using as the way to represent the position of this sprite on my screen, is the center of the rect. I could use the left corner, the right corner, the bottom corner. I can use the area, but I just need a point to represent where it is on the screen, and I'm going to use that rect center. but I'd like to have it as a vector 2. This allows me, again, to do the math, and so that's why I'm asking for it to get, that's why I have this hidden behind a property, so I can get the center and then very easily convert it into a vector 2 and send it back to whoever's the caller. Here's another property that gives me back the original position. I need the original position because remember, original position is the original location where the ball was. I'm going to have it go to some position and move back. And here is a setter. So this is the property that's like a getter, and this is the setter. So I can give it a new position as a vector 2 that will then translate that vector 2 into a tuple and assign it to my circle sprite's rect. My circle sprite's rect center. So this will change the position of the sprite. Here's how I'm going to get movement on the screen. It's like I have my position, I do some calculation, and I move the position to a different location. If I do this in small enough steps, you'll get the appearance of smooth movement. If I do it in jumps, it'll look like it's teleporting. I have another property to get the speed, and then I have another property that gets the inverse speed. The reason I have speed is I need speed to be able to calculate how it moves across the screen. When I click on a position, it moves to that position, and they all collect under the mouse. I decided for fun to do inverse speed so that when I click someplace else, the things that moved fast to that point will now move slowly back to where they were, and the things that move slowly to the mouse position originally will move fast back to in the other direction. Now, move_IP is a Pygameism. They have a lot of methods where they will put an _IP. _IP means in place. So move in place. If I call this method on myself and I give it a position, or I give an X and a Y, what it does is it changes my position by adding the vector XY to myself and assigning it back to myself. So I can tell myself to move by providing a displacement in the X and the Y direction, and then I'll move and change my own position. That's why it's move_in place. Sorry, move_IP, which means move in place. Contains is the method that is used to figure out whether or not the circle is the point that I'm given a point. I want to know if that point is within the circle of this this sprite. This is used when we want to generate the 1,000 random circles on the screen. It's very easy to generate random points, and then you check to see if that random point's touching anything. And if it is touching something, you just try again, and you keep on trying it very fast. Computers are so fast that it is better to just generate a whole bunch of samples than it is to try to computationally fit everything in place. And finally, I think it's a really good idea always to have some way to easily print out your values so you can log it, or you can try to debug by inspection by looking at what you see on the screen. And so I think it's a good practice to define the _str__ or the _REPR_. REPR is like the representation. So it will provide me a Python readable representation of that circle sprite. And that's good enough for me to understand what's going on and when I'm trying to make sense of what's happening here. So to recap, we've got two classes in this file. The two classes are circle sprite and circle surface. Circle surface is just the image, and this is the player character. I'll say player character or non-player character. And this class, circle sprite, uses circle surface to make itself look like a circle on the screen. Circle sprite is the insides, what it needs to know to be usable inside the game, and the surface is what you show on the screen. Okay, so now we've got these two classes defined. Let's go back to look at what else is in there. Actually, before we do that, let me just run this one more time. So every single one of these circles that you see on the screen is a circle surface. That circle surface is owned by a circle sprite, which is used by the game to figure out how to do this. When I click, it's going to produce a position, and all those sprites are going to figure out how to move to that position. Here we go. And then when I click anywhere else on the screen, all those circle sprites that are now collected on this one point are going to figure out how to move back to their original position. So if I select a different point right here, and I click, all the circle sprites have to figure out how do I move to that location. And as they do that, we update the display using the circle surface that each sprite owns. Let's do it. And then we click someplace else. They got to figure out how to move back to their original position. How does this happen? Let's take a look at the scene. So here I'm using I'm importing some math and random from the standard library. I've got my Pygame import. I'm importing these two things that belong to the video game project. Assets for finding the sound files and the soundtrack. RGB colors so I can find those random colors. And here, circles are not really something I export out, so I'm using a relative import by saying .circle to pull in the circle sprite. The circle surface is used internally by the circle sprite, so this scene does not ever see or talk to directly the circle surface. I've got a utility function right here to come up with a random position within the constraints of my window. So if I know my window's width and height, I will generate a position. You might, I think sometimes it's useful to just remind everyone that when you're thinking about pixels or images, if I say an image is 100 pixels wide, then I have a pixel location that goes from 0 to 99, and that's 100 pixels. If I say an image is 100 pixels high, then I can go from 0 to 99. So that's why oftentimes you need to remember to put that -1 there, because if you know how many pixels there are or how many things there are, remember if you start counting from 0, you need to go 1 less than. This is a very common mistake we make, and never hurts to remind those who might forget it from time to time, because if you forget it, it's okay. Just remember, be able to catch your mistake. So we're getting a random position here. That's just a utility function. Let's look at what classes we have here. We got 3 classes. We've got our base class scene. I've got that press any key to exit scene, so I have a way to exit out of the scene in case it gets stuck. And I've got my move scene, which does all the work. These 2 classes are identical to what you've seen previously, so I'll focus my attention here on move scene, which inherits from press any key to exit scene. Again, this was inspired by Go Over There. It's in the Pygame source code. That program is like 89 lines. It is very simple. It is just a tech demo where it shows you how you can do things, but it's not something that you can easily add more onto. And I think it's important for us to consider that as nice demonstration programs that show us how we can learn how to use a function or a class or some utility in a certain way. And then there's how do we construct something that's going to be able to support all the different features and bells and whistles that we want. So we've got our init, which is going to take a screen, which is what we're going to be drawing ourselves onto. That's our stage for our scene. How many circles? Defaults to 1,000, but we can always change that. We initialize our parent with the screen that we're going to be drawing ourselves onto, our background color, and here's where I get the soundtrack. The asset manager is something that I've discussed previously. It is just, it's a really simple, it's a file that has a dictionary, and it's got a get. It's got a little function that will get something out of it. It is not very sophisticated. It's not the best thing in the world, but it's a handy tool to use, so that way you can always get files relative to the location of this module. So that way, if you package up this repository and send it to another computer, or you send it to me, I'm able to get the same assets, the images, soundtracks, sound files, back out in a predictable way, and you're not hard coding fully qualified paths. That is a surefire way to make it not work. Let me give you an illustration of what I'm talking about. Here I am. Typically, you see me in this directory, in the same directory as move demo, and I type move demo, and it works. Soundtrack, sound effects. If I go into a different directory, let's say I get my home directory, I figure out where I'm there, and I go to some random directory. I go to my temp directory, and then I use a fully qualified path to the program. I still want it to work. You might say, oh, but doesn't it always work? It won't. If you don't use some mechanism that's going to generate the path at runtime, and if you use relative paths to where you're running the program, then it will break. And that's not a good thing, because when it breaks, it's going to cause your program to not run, and when it doesn't run, you can't get a good grade for it. So simple things like this, where I'm saying, here's how you do it. Please take the time to look at it carefully. If you've got concerns or questions, let's address them now, rather than deferring this, because I will tell you that I don't always run these programs from the same directory that you expect me to run them in. I have to run a lot of programs, so sometimes I run them from a different location, and that will identify problems like you using the wrong paths, or path names that map onto your home computer but not to somebody else's computer. So please make sure that you come up with either your own way to manage your assets, or use this toy one to get stuff done with. So moving along, our move scene is going to have some instance variables. It's going to have a target position. That's the place where I'm going to be clicking my mouse. So it starts out as none. I need something to measure how much time has gone by. I need delta. You've often seen this in your physics or chemistry, other science classes. Delta means change. I want to be able to measure how much time has changed, so that I know how much to move my little sprites by. So in between rendering passes, if a lot of time goes by, it needs to move more. If a little bit of time has gone by, it needs to move less. Oftentimes, when you start out writing simulations and graphics demos, or games, you don't consider that time is going by differently for every time you do a rendering pass. If if you're writing a game for like an Atari from the 1970s or 80s, your game is running at the clock. Everything's running according to how the clock works, and the clock in that machine is going to do like a one pass to render, one cycle to update everything in the game, and that's just how it works, because it's like it's not a multitasking, multi-user shared memory operating system. It's hardware that's doing one thing, and all the software is on that cartridge. When you think about writing software for a desktop computer, for a laptop, for a tablet or a smartphone, those devices have multi-user, shared memory, multitasking operating systems, and so your CPU time is part of part of all the different things that are going on inside the computer. So you're not guaranteed to get the same amount of time between each rendering pass. You might get something slightly longer, slightly shorter. That's why we're going to collect how much time has passed since the last time, so that we can move things according to how much actual time has gone by. Time according to our video games time. We need something to hold on to our circles. Here's a utility function that makes our circles. And then I have this instance variable represents all of our sprites. I take my circles. My circles are a list, inside that list is just my circle sprites. And I create this new object, which is a grouping of sprites. If you read the sprite documentation, it has how things can be grouped together. And in this game here, there's only one group, which is all the circles. But you can imagine if you're thinking of your classic arcade game, you might have one set of sprites be like your ghosts in Pac-Man, another set of sprites be the pellets, another set of sprites being the walls, another set of sprites being Pac-Man itself. And we don't have to deal with that in this because we have one set of sprites. So all my circle sprites go into this render plane, and I save that with my instance variable all sprites. Here are the two sound effects that I have. The second one, I use the same explosion sound. So I get that explosion sound and I set its volume. The sucking sound, it changes. And so I want to put a placeholder here to say, yes, that instance variable exists, but I'm actually going to figure out which one to use at runtime. And what I did was I wrapped this as a property. So if you ask for the sucking sound, it's going to randomly get that file, and I've got 3 of them, and it'll randomly select one out of the 3, set the volume, and then return that to whoever called it. Is this the best thing to do? No, because I have to like open a file every single time, so it's pretty slow, but it was an easy thing to get done. Make circles. So this is our utility function. It's not hard to digest, but what this is doing is it's creating a random, it's identifying a random position. So for every circle, I'm going to identify a random position, and I want to check to see if if it collides with any circles that I already have. So for every circle in my list of circles, I'm going to check to see if that circle contains that position, the random position I just did. If it does collide and the list of circles is not 0, then I'm going to do it all over again. I'm going to continue doing this forever until I get one that is not colliding. Now, it turns out it's not going to run forever. There is a point at which it will run forever, as if you give it an insane number. So with the screen size that I have, which is 800 pixel by 800 pixels, fitting 1,000 circles in there with a 3-pixel buffer won't take that long. If you go beyond that, it will go into an infinite loop, because then it becomes an impossible challenge to fit that many circles with that kind of packing. But this runs just fast enough for what we're doing here. And that's how we generate all the circles, is just generate positions, check. Generate positions and check. This is our getter and setter for delta time. Here's our process events. Now there's 3 events that occur. Let's review this by running our program. Event number 1 is you click on a position and all the circles move there. Second type of event is you click anywhere and all the circles go back. Third type of event is pushing R, which resets all the circles. Those are the 3 events. All the other events that are being processed are processed by the parent. And that would be like if I push escape. That's processed by the parent. So in process events, if my mouse button goes down, and if target position exists, then that means all the circles have already moved to that point on the screen. So I change that to none and play an explosion sound. I don't do any movement here because the movement doesn't occur when I process the event. Movement occurs because I've changed this state variable to a none, and that's going to cause update to behave differently. Update is the thing that gets called every click, every cycle through our loop that will change the position or keep the position of the sprites the same. Else, if target position is none, then I'm going to get the position of the mouse and convert it to a vector and store it into target position. So now I've got this position, a two-dimensional vector, and I'm going to use that to move all the sprites towards it. Because this variable has been set to something, my update is going to behave differently. And then I play that sucking sound. The last event that I have is reset. Reset is going to set the target position to none. It's going to remember how many circles to generate, get rid of all the existing circles, make all the circles all over again, and then update that container of sprites, and then the whole thing just essentially starts over again. All the hard work of making things move around or not move around happens in update scene. I call my parent because my parent might be doing something to update the scene as well. So I'm going to call my parent. Here's where I check to see if the target position exists or doesn't exist. If it does exist, that means that the circles need to move to that position. Here's the trick with doing this. Gotta run this one more time. If I want to get rid of the music. If I want to move to where my mouse is right there. If I want to move there, I need to imagine I'm one of the balls, one of the circles. And I'm going to move towards that mouse position. Every time you move towards that mouse position, you're taking a step. Now, how do you know when to stop? If you think about yourself in the physical world and you say, oh, I'm going to walk over to that spot over there. You're going to walk over to that spot and then you somehow magically know to slow down and stop when you get near that spot. That sprite also needs to have some sense of like, oh, am I close? Am I there? Should I slow down? Should I keep on going? And what happens if you overshoot it? In the physical world, if you overshoot it, you're going to go take a step back. Well, what if you overshoot it again? You're going to take a step forward, right? There's this adjustment. Our sprites aren't so sophisticated that they can like just take a step and get there. And here's a common gotcha with most of the time when I teach a course like this and students are trying to get something to move, they think I have something on the screen, I'm just going to move it to that position. And the first attempt that they do it, it pops. It pops from here to there, magically appearing. And they're like, that's not what I wanted. I'm going to break it down. So every time slice, I'm going to move it by some units. I'm going to move it 1 pixel to the left and 1 pixel to the right, so that way it's going to move diagonally. When that occurs, if your resolution is, if it doesn't work out perfectly, that it's going to end on the spot, you're going to overshoot it. And then when you overshoot it, you're going to say, oh, I passed it, I better turn around. And because the step, your step size is so large, you overshoot it again. Think about it. I point out a spot on the floor and I ask you to walk over there, but you must always use the same step size. And let's say you're forced to take large steps. If you step over that spot, you have to use the same large step size and step over it again. And you start hovering around it like one of those flies that buzz around your head. So we need to have some nuanced way to get everything to go to that spot and arrive there and not hover around that spot like a buzzing fly. And when we send them back to their position, there has to be a way for them to get to their position and stop and not overshoot it and act like a whole bunch of buzzing flies when they go back to their original position. That's why I think this demonstration is a good thing to practice and understand how that works. Because if we follow the idea of just like doing one step at a time, it's not going to work out the way we expect. So, I show you 2 ways you can do it. The first way, which is what we're using right now, is we're going to use move towards. Move towards is part of the math library that we can use to get stuff done, if I can find it. Move towards. Move towards returns a vector move towards a target by a given distance. The importance of this is it takes into account the current position the speed and how much time has gone by. And eventually when it gets there, it will stop. Now, the way we'd have to do this on our own, that's the else part. So if you want to see how this can be done without using move towards, is you want to say, what's the maximum distance you could travel in the amount of time that's gone by? I'm standing right here, and I know 1 second has gone by. So my speed times how much time tells me how much distance I'm going to move. But I need to see if that distance that I'm traveling, is it going to go beyond where I want to get to? So if I'm close to 0, this is my tolerance, then I want to continue, right? Where is the part where I want to point out to you? Here it is. So if my distance that I'm moving is less than the max distance, then I don't want to use that max distance that I'm traveling. I don't want to go that gigantic step. If the distance that I'm going to, which is calculated right here, I'm moving along this direction, right? How much can I travel? I'm moving along this direction. How do I calculate the direction? Remember your vector math. It's head minus tail. Where I'm heading to, the target position, minus my position. That gives me a vector from where I am to where I want to get to. This is where the mouse was clicked. This is where the circle's currently standing. This gives me a direction vector, and then I get the length of that vector. If that distance is less than what I can travel in the amount of time, then I want to just move my position to the actual target position and not overshoot it. Otherwise, I want to move proportional to how much I need to cover. So this is the direction vector, and I'm going to scale it by how much I can travel by over how much distance I have. And then I'm going to move my circle accordingly. This little bit of logic I encourage you to read carefully. And if memory serves, the reason I left the continues in there was to make the logic complete. Even though Pilot will complain about this, I shouldn't have put it in there, but I put it in there so that you can understand the thought process there. If you think the continues need to be removed, just remove them. But this one line is essentially this reasoning, and this reasoning is the important part of moving something on the screen. You don't want things to overshoot it. Now, this case is all because we've got a target position. Now, if we don't have a target position, meaning all the circles are on top of each other, and now we click someplace else, now we need to do the opposite. And so for every circle, we're going to do the opposite. We're going to move back to our original position. And instead of using our speed, we're going to use our inverse speed. And that moves everything back. How does everything get drawn? That's it. Sprites know how to draw themselves. All I have to say is to the container with all my sprites, draw onto the screen. Done. Finished. The hard work happens with maintaining state and managing things. So processing events is where I picked up whether or not I need to move someplace. Update is the one that is going to, update scene is what's going to change the instance variables for every single circle. And then every once in a while it just draws. And it will look like a nice smooth animation. Oops. Take a look. If we think about where our complexity is, the circle class is 100 lines. The scene does a lot of the work. It's twice as large as circle because it's got two different scenes. It's got the base class and then it's got the move demo. Game is another 100 lines. So this whole demonstration is like 300 lines of code. But a lot of it's repeated over and over again. So I'm using the same 200 lines from my previous demo that I gave you, the multiple scene one, and I'm just changing 100 lines to get a completely different outcome. This is the benefit of trying to abstract out repeated behavior so that you don't have to do everything from scratch every single time. So I hope this has been illustrative of how things work, and it gives you something that you can easily run and use and get an idea of how you can make things get animated and move around on the screen, and it looks cool. Try it out. I'll post a link if it's not already posted to this repository online so you can get a copy of it for yourself and try it out.